Guys, let's get started. Okay, today we have David Woodruff, and he's going to be telling us about strong coresets for kMedian and subspace clustering.
Okay, yeah, so thanks for inviting me, thanks for coming. So yeah, strong coresets for kMedian and subspace clustering, good by dimension. So we're going to talk about getting smaller coresets. These are data structures for solving clustering problems, in particular kMedian and kmeans, which I'll get into. So this is based on joint work with Christian Zoller. So what is the clustering problem? So the general goal is you have some input set. So here the points are these shapes. And you want to partition your input set into groups such that items in the same group are similar and items in different groups are dissimilar. Okay, so maybe I'm interested in clustering by shape. And maybe my clustering would put these triangles together, these circles, and these rectangles. But I might also care about some other measure. Maybe instead I care about colors. So in this case, the way I would cluster this is I would put all of the red items together, yellow, etc. So it is important to define your notion of similarity for clustering. And we're going to look at a few different notions. Though there are many notions that have been studied, here are some of them. So you might want to group points together to minimize the sum of Euclidean distances to their center, the center of a cluster. This is called the kMedian problem, which will be the focus of this talk. In the kmeans problem, you try to group the points together to minimize the sum of squared Euclidean distances to their center. So these are two standard variants, but you can imagine many other things. Maybe instead of Euclidean distance, you just have a metric space on your underlying points, and you want to cluster according to those distances. Maybe you have points on a sphere, and you care about things that have similar angle. You might want to look at cosine similarity. Maybe you have sets, and you might want to look at Descartes coefficient, distributions, maybe KL divergence. Many other notions have been studied for clustering. Okay. So let's look at Euclidean distance here. And as I said, Euclidean distance corresponds to kMedian clustering. So here's the formal problem definition. Your input is a set P. And I'm going to use n to denote the number of points. Okay, so I have n points, each in r to the d. So d is the dimension. And I'm given some number of clusters that I want to cluster with. So I'm given a number k. And I'd like to output a set C of k centers in r to the d. Okay, this is just k arbitrary points in r to the d, which minimize the following objective function. So cost of p comma c is just the sum over my n points of the distance of the point to its nearest center, okay, in my set C. So Euclidean distance. Okay, so here are my points, and maybe these are the centers of the clusters. In general, for the kMedian problem, if I tell you these are the points in a cluster, there's no nice sort of closed form solution for the cluster center. And yeah, so this is hinting at kMedian being a bit harder than another common distance measure, which is the kmeans problem. In this problem, it's the same setup as before, but now the cost function has just changed. Now you try to minimize the sum of squared Euclidean distances of the points to the nearest center. Okay, and kmeans has a lot of nice algebraic structure, and one nice property is if I tell you the set of points in a cluster, then the center is just the average of those points. Okay, is the mean of those points. Okay, any questions? Okay. So we're going to be looking at clustering in the context of very large data sets. So our point set P is very large. It does not fit into main memory, for example. And one way of coping with this is to design algorithms for clustering that are distributed or in the data stream model. And I'll describe what both of those models are. I want to emphasize that we're going to consider the case when we have a moderate number of clusters k. So you can think of k as being a constant, maybe, or something very small. But we have very high dimensional data. Okay, so both n, the number of points, and d, the dimension, are very large. Okay. So high dimensional data has motivated the notion of a coreset, which is the following. So we'd like to compress our input set P to a small data structure. And in particular, one form that is often looked at is we'd like to compress it to a small weighted set S of points. Okay? And I'll describe this more. Such that S approximates P with respect to the problem of interest. Okay, so we'd like to replace our original set P of points with a set S of points, a much smaller set S of points. But we might also attach weights to the points. Okay? So there are many different notions of coresets around. We're going to use this original definition by Har-Peled and Mazumdar, which says that this weighted set S is an epsilon k coreset for a set P of points with respect to, say the kMedian or kmeans problem, if the following holds. So I'm going to call this the for all guarantee. What it means is that for all set C of k centers, so any set C of k points in R to the d that you might choose, you have the property that the cost of using C to cluster the points in S is within a 1 plus or minus epsilon factor of the original cost of using C to cluster the points in P. Okay, now what does cost here mean? So let's look at cost of P comma C. So I'm going to be thinking of P as an n by d matrix. Okay, the rows correspond to my n points. And the cost of P comma C, well, I take each row, each point, and if it's kMedian, then I just compute its closest center, and I sum up the Euclidean distances across those n rows. That's what cost of P comma C means. And if it's kmeans, I would sum up the squares of the Euclidean distances to the nearest centers. Okay. Now, cost of SC, if S were unweighted, this would be the same thing. Okay, so S has some number of points in it, and I just do the same thing with this small set S. I just sum up the distances or the square distances, depending if I'm looking at kMedian or kmeans. Now, I do attach weights. I do allow myself to attach weights to the points in S. So if I have a weight W for some point, then I sum up W times the cost on that point. Okay, so if some point is weighted by W, I look at its distance to its nearest center, that's some distance, and I multiply that by W and compute the summation. Okay? So just some things to note here. Really what I want here is the for all guarantee. Okay? I want to find this set S so that now for any set C of centers, I can use it to approximate the cost on the original point set. So in some sense, I can throw away my original point set now. Okay? Yeah?
So S and C subsets of P, or they're in ambient space?
No, they're not necessarily subsets of P. Yeah. So these are just in the ambient space, arbitrary. Yeah. Question? Yeah.
For the k-means problem, when you tap the weighted, is it just kind of like a weighted mean is the appropriate center to choose, or is it more complicated than that?
Yeah, so you can fold. Yeah, so for these cost functions, you can sometimes fold the weight into the cost. Yeah, but other things that are not scale invariant, you can't do that. Yeah. Any other questions? Okay. Okay. One property that you might want about coresets is composability, and what this property is the following. If I have a coreset for the set P and a coreset for the set Q, I should be able to merge them to come up with a coreset for the set P union Q. Okay, we'll see why this is a useful property now. So here's one of the settings for dealing with large data, a distributed setting that I mentioned. So suppose you have too many points to fit in main memory on a single machine. A natural thing you can do is take the points and partition them across multiple servers. Okay, so maybe if I have enough servers, now each server can store the set of points in main memory that it holds. Okay, so but you still want to cluster the union of all the data. So you want to come up with a clustering for all the points. And the natural way of doing this is for each server to compute a core set of the points that it holds locally. Okay? And so each server computes a core set of its local data set, and it sends the core set to some central server. Okay, so you see that the communication in this protocol is proportional to the core set size, which is one motivation for trying to achieve small core sets. This central server can then take all the core sets it receives. It can stack them together, and this will be a core set for the union of all the points. Right? If I can approximate the cost of using some set C of centers on this, I can add it to the cost of using some set C of centers on this, and so on. And so I get a core set for the union of the data points. Now that naive thing of just stacking the core sets together might be very large if I have a large number of servers. So it also might be beneficial for this central server to take the stacking of the core sets together and compute a core set of that. Okay, so this is like computing, this is this composability property that we talked about on the previous slide, right? If I have a bunch of core sets, I can compute a core set of that, which will be a core set for the union of the points. Okay? Okay. So that's distributed algorithms. Another large data setting is streaming algorithms. So here, in this context, I see points one at a time in the stream. And after seeing some number of points, I have too many points to fit into memory. So what do? I compress them a little bit by building a core set of those points. So maybe I've seen some number of points, say t points, and maybe I would compress them down to t over 2 points in a core set. Maybe I would use half of the amount of memory I need to store the points by building a core set. Okay, so I build this core set. And then I see another set of points in the stream. And I build a core set for that. Okay? So I've thrown away these original points, and I've only stored these core sets. Now I have these two core sets, and what can I do? Yeah, I can compute a core set of the core sets. Right, by this composability property, I can merge these and get another core set.
Your epsilon's growing, right?
Yeah, your epsilon is growing. So let me get back to that in a minute. Now I see some more points in the stream, compute a core set, some more points, another core set of the core sets, core set of the core sets of the core set, and so on, right? So the nice thing about this is, what is the memory of the streaming algorithm? Well, I'm only storing a core set, at most one core set for each level in this tree. Okay? If I see n total points, then I'm going to have log n levels in this tree. Okay, so my memory will be log n times the core set size. Now let's go back to a question, which is, what about the epsilon dependence, right? So suppose this core set gives me a 1 plus epsilon approximation for all queries for these points. This core set gives me a 1 plus epsilon approximation for all queries in these points. Well, when I compute the core set of the core sets, then I'm going to get a 1 plus epsilon approximation to these 1 plus epsilon approximations. So it'll be like a 1 plus 2 epsilon approximation. So I have a 1 plus 2 epsilon approximation here, a 1 plus 2 epsilon approximation here, and now I'm going to compute a core set of that. And so I'll get a 1 plus epsilon approximation to what was a 1 plus 2 epsilon approximation. So I'll get a 1 plus 3 epsilon approximation, and so on. So in general, you do have to adjust your epsilon, but you just replace it with epsilon divided by log n, where log n is the depth of the tree. Okay, so it's not a huge loss there. Okay, so yeah, so this is called the merge and reduce framework in data streams. Any questions about that? I mean, there's also, if you have a randomized construction, you might have some failure probability, but you can sort of union bound that away. Okay, cool. So yeah, so natural question is, what is the optimal Coreset size for these different problems? Okay, so here is the work that has been done on the kMedian problem. So in that original paper of Harpaled and Mazumdar, which introduced this notion of coresets, they gave a coreset for the kMedian problem of size k log n over epsilon to the d. Okay, now for us, d is going to be very large. So even like a linear dependence on d, we don't want. They're getting an exponential dependence on d. But they were motivated from a computational geometry, applications where d was typically small and constant. This is not the setting that we're in. Okay, so we're in the setting of you have many features. Your feature space is very large. The first improvement to this was getting rid of the log n. Okay, by Harpaled and Kushal, they got k over epsilon to the d. And this is qualitatively very interesting. Like your coreset size doesn't actually have to depend on the original number n of points. Okay, but it's still exponential in the dimension. Chen later improved this to bring it down to linear in the dimension, but the log n factor came back in. Langberg and Schulman then got rid of the log n factor, so it was polynomial in k, d, and epsilon. And the state of the art before this work was due to Feldman and Langberg, which got a coreset size of kd over epsilon squared. Okay, so yeah, question.
Sorry, these are all algorithmic results, not just existential?
Yeah, these are algorithmic results.
Are they
yeah.
randomized algorithms typically, or?
These are typically randomized, yeah. Okay, any other questions? Yeah, Jason.
Wait, if it's randomized, does it succeed with probably constant then, or with high probability?
I mean, one way of doing this is like to get a randomized algorithm that succeeds with very high probability and union bound over like sort of a net of centers, and then sort of like it's still very high probability because yeah. Question, Anesh.
So if you have this composability property, do you restrict yourself to having a linear sketch of the data, or can you do something that is not just?
So there are data structures that are composable that are not linear sketches. Yeah. Question.
So that was originally done to remove the log n, was instead of union bounding over like n points, a union bound over a net, which is.
Yeah. So this is coming from a net argument. But I think it is a little bit more involved. Yeah. Any other questions? Yeah, Nihar.
So this is a coreset for kMedian.
Yeah.
Just curious, like if you have a coreset for kMedian and I also want something for kmeans, suppose I have two coresets. If I take a union, is it a coreset for both these costs?
No, I mean the kMedian costs could be very. I mean it depends like what you mean by taking a union. Like you want to take both of them and evaluate them, together on some point set.
That's my size S1 union S2. That's
Yeah.
my S prime.
Okay.
So overall my goal is I have a single machine and I want to compute kMedian or kmean depending on whatever the user decides. Right, so I want a coreset which represent which.
I mean, if I have both, I can choose which one depending on the query.
Yeah.
But if I actually want to like combine them into the same estimator, yeah, because the kMedian cost could be much larger than the kmeans cost. Yeah, or vice versa. Yeah. Okay, so the main question that we had in starting this work is, does the D need to be here? Maybe it's possible just to have a coreset which is only a function of k and epsilon. Maybe it's polynomial in k over epsilon, independent of both d and n. Okay, and that's actually what we show. So our main result is there's a coreset with this for all guarantee that I've described for the kMedian problem, with a number of points that is independent of both n and d. And moreover, the size of this coreset is a polynomial in k over epsilon. Okay? So that's the result. The way we achieve this is via two steps. I'm going to go over a dimensionality reduction for kMedian. Okay, so what we're going to do is we're going to start with n points in Rd, and we're going to end up with n points in actually a little bit larger dimension, Rd plus 1, but they're all going to sit in a very low dimensional subspace. Okay, this is the strategy. This will be what I'm calling dimensionality reduction. So I'm going to have n points that sit in roughly k over epsilon squared dimensional subspace after I apply this dimensionality reduction procedure. After I do that, then I'll just be able to apply off-the-shelf existing Coreset algorithms, which achieve, for example, the Feldman-Langberg result that we just saw in the previous slide. They achieve a number of points which is linear in the dimension times k over epsilon squared. What have we done? We've replaced the dimension with k over epsilon squared. So if you just compose our dimensionality reduction result with existing Coreset techniques, we'll get a Coreset for kMedian, which is independent of n and d. Okay, so this is the strategy. Questions? Okay. Yeah. Okay, so the outline for the talk. I'm first going to present a new proof of an earlier result of Feldman, Schmidt, and Zoller. So I want to mention that this result, having a Coreset of size independent of n and d, was known for kmeans. Okay? And it was an open question for kMedian. So it was shown in this paper for kmeans. And it used a very algebraic approach specific to kmeans. I'm going to give a different proof of that, which is a little bit more geometric. And that still won't quite work for kMedian. But we'll show how to adapt it to make it work for kMedian. Yeah. Question? Do you have a question? Okay. Okay. Okay, so just to make sure we're all on the same page here, we're going to use the Pythagorean theorem over and over again. Let me just couch it in this context. So yeah, so what we have here is we have some subspace T, which I've drawn as a line. So it goes through the origin. It's a subspace. And we have some point P, okay, just some arbitrary point P. And okay, so in this picture, P prime is the closest point to P in Euclidean distance, the projection of P onto T. And here's some arbitrary point Q in the subspace. And the Pythagorean theorem is telling us that the distance between P and P prime, A, plus this distance B, so we have A squared plus B squared equals C squared. Okay? Pythagorean theorem. Okay. So if in particular, like if I have a point Q for which this distance C is very close to this distance A, then it actually means that Q is very close to the projection of P onto that subspace. Okay, so this is just some intuition to keep in mind. Okay. So here's the main dimensionality reduction algorithm that we give. So let's go over this slowly. I'll first describe it just as an existential algorithm for, okay? So let opt be the cost of the optimal k-means clustering. Suppose you know it somehow. Okay, what do? We start by computing the optimal k-dimensional subspace S in R to the d, which minimizes the sum of squares of distances of our endpoints to it. Okay, so we look at all k-dimensional subspaces. We try to find the one which minimizes sum of squares of distances of our points to it. Okay, does anyone know what that space S is? Yeah.
The top k eigenvalues.
Yeah. So, right. So these are the top k principal components. Right singular vectors of your matrix. So it is in fact you can in fact find this. This optimal space efficiently in this case. Okay, so I find this subspace S minimizes sums of squares of distances to it over all k-dimensional subspaces. Then what do? Okay, I run the following while loop. While I can add k dimensions to S, right? So S is starting off as a k-dimensional space, and I'm going to add k dimensions to it. While I can add k dimensions to S to reduce the cost of the subspace approximation problem. So what that means is the cost is the sum of squares of distances to the subspace. So while I can find k dimensions which reduce the cost by an additive epsilon squared opt, I do it. Okay? And so I start with k dimensions, that's S. I find some k dimensions I can add to it. I have 2 k dimensions, and maybe the cost went down by epsilon squared opt. Then I do it again. Now I have maybe 3 k dimensions, and the cost went down by epsilon squared opt again. So how many times can I do this while loop? 1 over epsilon squared times, right? I can't have a cost less than 0. Okay, So the final dimension of my space S is then k over epsilon squared, right? At most k over epsilon squared.
I'm confused.
Yeah.
So the original projection, of course, could give you very short distances, but nothing to do with the original data, right? I mean, intuitively that, it all projects down into where everybody's very close. And so what do you mean by finding the next subspace?
Oh, I mean, yeah, so I mean,
You want to make the distances expand back out so they're better closer to the real distances?
that's right. Like, so you could think of these distances as being like further down in the spectrum, for example. Like you're trying to, I mean, your query centers could be arbitrary, right? So like, I can't just, maybe the question is, can I just stop with step 2?
No, it sounds
yeah.
like it's terrible.
Yeah, okay, good,
It
yeah.
could be that everybody's all on the same point or something.
Exactly, yeah, exactly, yeah.
So,
And so if I
but I don't
yeah.
understand what step 3 is doing. I don't understand step 3.
why it's-
So that they expand back out?
Why it's working. Okay, I mean, you understand the step, you just don't understand the intuition.
No, I don't understand what it is.
Oh, even the step, okay. Yeah, so let's go over this. So yeah, I have a k-dimensional subspace S. And what I try to do is I try to find at most k dimensions to adjoin to this space. So now it'll be at most 2 k dimensions. And I try to do that, I do that only if this reduces the cost by epsilon squared opt. Okay, so the original cost, I had this space S, and I had the sum of squares of distances to it. And I had some cost. Okay?
That could have been very small compared to the opt, right? Could you project it?
I mean, it could be opt, right? It could be opt. Right, so there are 2 things here. One is like, okay, there's another, okay, here's the question. So first of all, why is this, why is the cost of using this subspace less than or equal to the k-means cost?
Oh, I see. Yeah, that's true. I see. Okay.
Yeah, because one thing you can do is you can take your k-dimensional space to be the span of your k-means, right? That's one particular k-dimensional space. Okay, but is this step clear here? Yeah, Anesh.
Is there like a short description of what k dimensions you add to S?
In the k-means, yes. You would start with the top k principal components, then you would take like the next k principal components, etc. For kMedian, no, but I'll get to that later. Yeah. Okay. Any questions? Yeah, Raj.
So for kMedian, the problem of finding the S is going to be non-clear.
Let's postpone that to the kMedian part of the talk. Yeah, yeah. Any other? Okay. Okay, so the algorithm's clear. What do you do in the last step? Well, you found the space S, and now you take your points P and you project them onto S. Okay, so I still have endpoints. I'm still an R to the D. But all these points, they live in this k over epsilon squared dimensional subspace. Okay? And I also output a scalar, which is crucial for this algorithm. So this scalar delta is the cost of moving my endpoints to the space S. Okay, so I have this space S. I'm taking all my endpoints and I'm moving them to it. And I'm taking the sum of squares of those distances and I'm calling that delta. Is that clear? This is the cost of, the sum of cost is square distances here. This is the cost of moving the points to the space. And now these are the points inside of the space. Okay, that's all you output in this Coreset construction. Yeah, and as I said before, like this opt, you just need it to be less than the original k-means opt. So this is, the opt that you start with here. It's not changing in each iteration, right? It's the fixed opt at the beginning. Okay. Okay, so here's the analysis. Here's my original point set P, and here's an arbitrary set of centers I query C, k centers. So ignore this squiggly stuff for the moment. Let me define T to be the span of the set S that I found with the subspace S I found with dimensionality reduction, together with the set C. Okay? So T is just used here for the proof. P sub T is the matrix. Each row is the projection of the corresponding row of P onto T. Okay, so here's the picture. Like I have, I've drawn it as a plane, this subspace T. Here's a point P. Here's its projection P sub T onto T, the closest point. Now S the subspace S that I found with my dimensionality reduction procedure, it lives inside of T. So I drew it as a line here inside of this plane. Now here's the projection of P onto S, P sub S. Right, the closest point in S. And here's the closest point in T. And since S is contained inside of T, I mean, I have this Pythagorean theorem here, right? The cost of moving P to S is the cost of moving P to PT plus the cost of moving PT to PS, where cost is square distance. Okay, okay, so here, it's important that T contains S. Okay, so that's the setup. So does someone know why this first equality holds? The cost of serving the points in P by C is the cost of P comma T, so moving the points P to T, plus the cost of the projections of the points inside of T and moving them to C. Why does this hold?
The cost of sum squares.
Yeah, this is the Pythagorean theorem, right? Okay, good. Okay, so that's the actual cost. Now, I threw away my original points, right? I built this Coreset. I don't know what P is anymore. I mean, I don't know what cost of PT is. And I don't have projections of P onto T. What do I have? Well, I have cost of P comma S. That was this delta, this scalar in this dimensionality reduction. And I have my points projected onto S. That's what I did in dimensionality reduction. So if someone gives me C, I can compute this cost. Because I have these points, and for each point I check who's the nearest in C. So I can compute this side. And I can't compute this side with my Coreset. But the claim is that these two things are close to each other, the left-hand side and the right-hand side. Okay, yeah, Jason.
Wait,
Yeah.
so when you have a delta, you just add delta onto your solution and answer? Is that allowed?
Yeah, that's allowed. Yeah. Questions? Okay, let me just sort of summarize what I said on the previous slide. So we want to split the k-means cost into two parts. The cost of projecting the points onto a subspace T, plus the cost inside of the subspace of moving those projected points to the centers. So T contains the set of centers. That's why you have this Pythagorean theorem. And it's used only for analysis purposes. And the point of this subspace S that we found with our dimensionality reduction procedure is we want it to work for all T. Okay? So we'd like the projections onto S to be close to the projections onto T for any T that you might choose. You can choose different T's depending on which centers you choose, right? So it's going to be important that T contains S. Okay, so let me just go back to the analysis. Yeah, Raj.
So this is just going to allow you to approximate the objective function. Are you going to get centers in the original Rn or Rd out of this?
You can get centers in the original.
Okay.
Yeah. I mean, I haven't even. I'm actually in this k over epsilon. I'm actually still in R to the d. I just said that they're living in k over epsilon squared.
Subspace.
Yeah, but you can store like the subspace S to go back to the original space. Yeah. Okay. Okay, my first claim is that cost of P comma T is very close to cost of P comma S. Does anyone see why? Yeah.
If it wasn't close, we would have added on the k dimensions corresponding to C and got P instead.
Yeah, exactly, right? By definition of the algorithm, dimensionality reduction, right? Like if cost of PT were significantly less than cost of PS, more than epsilon squared opt, then we would have added, we wouldn't have stopped the algorithm, right? And we know that cost of PT, is at most the cost of PS, right? T contains S. So T improves S by at most epsilon squared opt, so these two quantities are similar. Okay, what about these other two quantities? Okay, so I'm not going to give the full argument for k-means. I will give a full argument for kMedian, hopefully. So here's the picture again. So this center C is just somewhere in T. Here's P, PT, and PS. So since the subspace S is inside of T, the square distance of a point P to S is the sum of square distances of P to T and of PT to PS, right? That's just the Pythagorean theorem. So as you told me, cost of PS is equal to cost of PT plus cost of PT comma PS, right? That's just Pythagorean theorem again, right? It's the cost of moving P to T and moving that projection to the projection onto S. Okay, that's this first line. So just rearranging here, I get the cost of PT comma PS is the cost of PS minus the cost of PT, which is at most epsilon squared opt, right? Because otherwise T would have improved the algorithm. Okay, so what this is telling me is that on average, the projections of the points onto T are close to the projections of the points onto S. Right? And what you can show is, if you do have this property, this on average property that the projections are close, then you can actually show that the cost of using the projections in S with some query set C is about the same as the cost of using the projections of the projections onto T with some query set C up to epsilon opt. Okay, it's a simple proof. It only uses Pythagorean theorem. I'm not going to do it, but you lose an epsilon. You go from epsilon squared opt to epsilon opt when you do this. So what this shows is that this term is also very close to this term. Okay? And that's all we need. So this implies, in particular, that this left-hand side is within additive epsilon opt of this right-hand side. Okay. So this reproves this theorem of Feldman, Schmidt, and Zoller, which is the following. So let A be a matrix storing n points from R to the D as its rows, and let A sub m be its m rank approximation for some m which is order k over epsilon squared. Okay, so all they're doing is computing the SVD, the singular value decomposition, and taking the top k over epsilon squared components. That's actually what our algorithm would end up doing. So we have the same algorithm, and what is our cost? Our cost is the cost of moving all of our points to the subspace. That's this delta, which is actually the rank m cost, the cost of approximating A by the best rank M matrix. Okay, so we're reproducing this algebraic result geometrically, and yeah. So what they show is that if they use this scalar delta, then you have the property that for all sets of centers C, the cost of moving the projected points onto this space. I mean, I take my points, I projected them onto the space. I get A sub m, and the cost of using A sub m with query center C plus this scalar delta gives me a 1 plus epsilon approximation to my original problem. Okay, yeah, question?
In your algorithm, there was a step where you wanted to check if adding k new dimensions
Yeah.
contributes epsilon squared times opt.
Yeah.
Can you do that algorithmically without knowing what opt is?
Oh, yeah. So no. So you need to figure out what you just need a lower bound on opt. So you don't need to use the kmeans opt. And one way of getting a lower bound on opt is just to compute the SVD, right? Yeah. So it can be done efficiently. And in fact, you can do it much faster than SVD using randomized SVD. Okay. So that's the result. Any questions about it? Okay. So now I want to move on to kMedian. So we don't have, I mean, of course we still have that, c squared is a squared plus b squared. And we still have, this intuition that if the distance from a point P to a point Q in a subspace is close to the distance of P to the subspace, then, the 2 points Q and P prime should be close to each other, right? It's the same intuition as before. But the problem is we can't simply split the cost into the cost of projecting the points onto the subspace and then the cost of moving the points in the subspace to the centers. we don't have this Pythagorean theorem anymore. We don't have sum of squares. Okay, so that's the main issue here. Is the issue clear to everyone? Okay, cool. Okay.
Because it's false?
Yeah, so I'm going to give a counterexample. Great. So as Gary predicted, this next slide, in fact, you cannot hope for a k-means type guarantee that we had before for the k-median problem. Okay, so what I mean by that is, what if we wanted a guarantee like the following? We'd like it to be that we can find a low-dimensional subspace S so that we can project all of our points onto this space S. And then, we also have some scalar delta. And then someone comes along and gives us this query set of centers C, and we just plug it into this formula, and we get a 1 plus epsilon approximation. I claim that these kinds of corsets don't even exist for k equals 1 for the k-median problem. So let's see why. Here's a counterexample for one median. Okay, so suppose your point set is a random set of n points on the unit ball in R to the d. Okay, so I've drawn it here. It's centered at the origin, and I've chosen a bunch of points on this unit ball. Okay. Now, suppose I chose some fixed m-dimensional subspace S, where m is small. It doesn't depend on n and d. Okay? Now I'm choosing these n points at random in P. So what are the projections onto S going to look like? So this is the unit ball. They start off with norm 1. For the moment, just suppose I'm fixing some m-dimensional space S. M is really tiny. But what is it? Yeah, they're Gaussian, but like what is the norm of the points on this subspace? Typically, very close to. No, it's not. No, it's not going to be 1, right? Yeah, it's like the squared norm is like k over m, is m over d, right? And I have an m-dimensional subspace of R to the d. So if I take this random space, if I take a fixed space and I take a random point on the sphere and I project it onto it, my squared norm is going to be about like m over d, which is like super tiny, right? It's very close to 0. Okay, so like the sum of squares the sum of squares of the norms is going to be like very tiny. Okay, much less than the original n, which was the sum of squares of the norms. Okay. Now that was for a fixed subspace, but this is a super high probability event, right? I mean, I can choose my number n of points to be very large, so large that I can actually union bound over all m-dimensional subspaces. So for any m-dimensional subspace you come up with, it's going to be the case that almost all of my points have norm very close to 0 when they get projected onto this space. Okay, is that clear? Okay, cool. Yeah, so that's all I've written here. If the dimension d is much larger than the dimension m of the subspace, then the projected points, almost all of them have very tiny norm. But what if in this case someone gives me the query center, which is the origin? So this quantity here is going to be super tiny, right? Like I'm putting the origin here, and all of these things have really, almost all of these things have really tiny norm. This thing is very close to 0. But what is the actual cost if this is the origin? What is the actual one median cost? It's n, right? Like everything here has unit norm, so it's n. So what does delta have to be? I mean, if this is going to be a good 1 plus epsilon approximation, delta had better be very close to n, right? Okay. Well, on the other hand, what if I have the query which is some particular point on this unit ball? So my center is not the origin anymore. It's some particular point on this unit ball. And let me just call it 1, 0, 0, 0, right? That's my query point. What's going to happen? What is the one median cost of using this center? Yeah, square root 2n, right? Because it's some particular point on this ball, And like almost, I'm choosing random points. Almost all these points, almost all these distances are going to be square root 2, right? And I have n of them. So the actual cost is like square root 2n, right? OK, but what's going to happen here? Well, delta, we said, already had to be n. And what is the cost of moving my projected points on S to this query center C, which is on the ball? It's going to be about n, right? Because all my projected points, they have norm, which is about 0. I mean, not all of them, but almost all of them. So all my projected points, they have norm, which is very close to 0. And I have to move them to this point on the ball. And I have n of them, so it's n, right? So this cost is n, delta is n, so the value of the data structure is close to 2n. But the actual cost is root 2 times n. So this sort of rules out 1 plus epsilon approximations for data structures of this particular form, okay, of the same form that we had for kmeans. Is that example clear? Question?
What's wrong with the third bullet? Why did you need a fourth bullet?
Oh, I mean, well, I need to have more than just one query center, right? Otherwise, I can just have delta be the solution for that one query center, right? Like, I mean, like, what do you mean? What's wrong with it? Or?
Well, no, yeah. Why isn't that just a counterexample? Why did you go to a IC?
Well, I mean, if delta is n, and this is the query, the origin, then it's valid, right?
Oh, I see. Okay.
Yeah, yeah. Okay. Any other questions? Okay. Okay, we're not going to get a data structure of exactly that form. Okay. So the main idea here is we're going to add a new dimension to each of our points. Okay, we're going to add an extra special dimension to each of the projected points that is going to encode the distance of that point to the subspace S that we find with a procedure which is similar to this dimensionality reduction procedure. Okay, so I'm going to get into that. Let me just skip the solution here and just give you the algorithm to make it clear. Okay, so here's the dimensionality reduction algorithm for kMedian. So let opt be the cost of the optimal kMedian clustering, just like as before for k-means. And let's compute the optimal k-dimensional subspace S, which now minimizes the sum of distances of points to that subspace, okay, instead of sum of squares of distances. This is just going to be an existential result for now. There are approximation algorithms that do this, that actually suffice. But let me not get into that. I just want you to understand this like structurally. Okay. So what does the algorithm do? It has the same while loop. While we can add k dimensions to S to reduce the cost, which is now sum of distances, while we can add k dimensions to S to reduce the cost by additive epsilon squared opt, we do it. Okay, just as before. Yeah.
I'm missing something here. Do you not know opt?
Yeah. So I'm describing this as an existential result for now. You can get very fast algorithms for this. You don't need to know opt exactly. You can get an approximation to opt, and you can get an approximation to this initial subspace as well. But let me not get into that right now. Okay. So you're going to do this iteratively. You're going to adjoin k dimensions. You're going to keep doing it, and you'll do it at most 1 over epsilon squared times, just like before. Okay? I mean, right? Clear? Okay. The only thing that's different, I mean, besides the cost measure being different, the only thing that's different is the fourth step. Instead of just returning the projection of your points onto this space S together with this scalar, what you're going to do, for each point P in your input set, you compute its distance to the space S that you found. Okay? And what do you return? You don't return a d-dimensional point. You return a d+1 dimensional point. So you return the projection of that point onto the space S, just like for k-means. But you have one extra dimension which encodes the distance of the point to the space that you found. Okay? That's the whole, that's the algorithm. Is that clear? Yeah. Oh, question.
You could have done the same for k-means and remove.
You could have done the same thing for k-means, and since you have sum of squares, you could pull all these out and you would get a delta. Yeah.
You mean W0 or?
No, you would get this cost, sum of square distances of your points to this space S, right? Delta was like the cost of p comma S, right? So that's what you would get. But you'd get the sum of squares of these things. You could move them all out. But you can't move them out for kMedian.
What I mean is you can set delta to 0.
Oh, you just want a different algorithm for k-means and putting them inside of the, yeah, you could do that, yeah. In fact, this, one thing I didn't mention is that all this generalizes to sum of pth powers, including sum of squares, so k-means, yeah.
So just to make sure I understand, so if we're in 3 dimensions and S is 1-dimensional, we're taking all the distances of the things to the line, and we're just viewing that, we're projecting that down into a 2-dimensional problem?
That's right, yeah, so we have the project.
So we're going to take all this 3D data, we're going to project it all down into a line, so now we end up with some kind of, and I see, and they're all positive distances, you don't have anyone
That's right.
below the line, right? So
The second coordinate is always positive, is that what you're saying? Yeah, or non-negative, yeah. Okay, why does this work? Same picture as before, okay? Nothing changed. So let T be the space, again for analysis purposes, containing the query center C and the subspace S that you found with this new dimensionality reduction procedure for kMedian. So the first lemma that we show is close projections. So this lemma for k-means, do you remember why this was true? Like the cost of, so I project my points onto T, which is, the space S union the span of the centers, and I project my points onto S, and we argued that the cost of PT comma PS was small. Now for k-means, that was just the Pythagorean theorem, right? For kMedian, this is a little bit more work because it's sum of distances. But again, all these things, they just come down to very elementary arguments. So should I do it? Sure. Let me just give you a flavor of how you prove this. So what you can do, actually, let me skip it. So all this is going to use is the basic property that S is started off as being an optimal solution, and that you can't augment S by k dimensions and reduce the cost by more than epsilon squared opt. Those two properties, together with Pythagorean theorem, are enough to prove these kinds of statements. Okay, I'm going to skip that. Yeah, so I mean, you can sort of, anyway, not so important, but this is just some inequalities. That's one thing. The next thing you show is that a distance to subspace lemma. Okay, so we'd like to show that cost of PS minus cost of PT is at most epsilon squared opt. Okay, so this is immediate. Why is this? It's the same reason as before, that otherwise T would improve the cost by too much. Okay. The other thing you need to show is that if you take a point P in your input, and C sub P is its closest center in C, then we have this lemma which I call distance inside of subspace. Okay, so what do we want? We'd like that if we use the projection of the points onto S instead of the projections on the points onto T, which we don't have, then the distances to the centers are roughly the same. So basically, we can swap out the projections onto T with the projections onto S. So meaning that the sum of absolute values of differences is at most epsilon opt. This is the proof here is just triangle inequality. So the distance from point PS to the center CP is at most the distance of that point PS to PT plus the distance of that point PT to CP, triangle inequality. And I just take the difference, and I get that this sum of absolute values of differences is at most the sum of the distances between the projected points on S and the projected points onto T. And that was our earlier lemma on the previous slide, that the cost of PSPT is small, right? Like all the projected points onto S are on average close to the projected points onto T. So you just use triangle inequality and that lemma on the previous slide, and you get this other lemma. Okay, so these are simple lemmas, but let me just give you the punchline. Like, how do we put this all together? You know, what is the main reason why we wanted to add this extra special coordinate? Okay, what is the original distance p to its closest center? Well, by Pythagorean theorem, it's the square root of the square distance of p to pt plus the square distance of pt to the center cp, right? Here it was important that t contains the center. Okay. And what do we want to compare this original distance to? Well, what did we output in our Coreset? We outputted the projected point p onto S, and we put in a dummy extra dimension, which was the distance of p to that subspace S, right? So we have a d plus 1 dimensional object. And how do we handle queries? Well, someone gives us some center, C, and we put a 0 on the extra dimension that we've added. Okay, that's how we algorithmically define how we answer queries. Okay, so this is the distance in our data structure, and this is the original distance. Well, what is this distance? Okay, well, it's the sum of squares of, I have this point and I have this point. So I can first look at this number minus 0 squared, and I get this thing, right? And I get plus the distance from PS to CP squared, right? Is that clear? Right, so I'm just taking this distance plus this distance squared plus this distance squared, square root. That's my Euclidean distance of these new points. Okay, so this is my actual distance, and this is my distance in my Coreset. And now you should notice some things here. Like, here we have distance of a point P to the space T. Here we have distance of a point P to the space S. If we didn't have the squares, then we know that, like, on average, these things are small, right? This thing is very close to this thing. That was this lemma on the previous slide, like distance to subspace lemma. And what about the second thing? Well, this is the distance inside of the subspace, T, to some center. And this is the distance inside of what we actually have, our space S, to the center. And again, we know that on average, this thing is close to this thing. I mean, it's squared here, and there's a square root around everything, which makes it a little bit annoying. But if there were no squares and square roots, then if I just took the difference between these two things, then I would just be taking the sum of differences of these plus the sum of differences of these, and by both of the lemmas on the previous slide, this would be small. Right? So the only thing is that, okay, we have to deal with squares and square roots, but again, so just let me emphasize here that if I were just to sum these without the squares and sum these without the squares, the difference here, I would get cost of PT in one case and cost of PS in the other case. And they're about the same by the distance to subspace lemma. And if I were to do the same thing here without the squares and just take the differences, then by this distance inside of subspace lemma on the previous slide, this would also be small. And so overall, I would get that this distance is about this distance. Okay. Now there are, as I said, you actually do have squares, but you can use some basic inequalities again that I really didn't get into in this talk. To roughly, the idea is to convert like an L2 distance to an L1 distance. I won't get into it here, but this is the main intuition. Okay, you lose a factor of epsilon when you do this, and so this sort of captures the reason why you wanted to add this extra dimension, right? Because this extra dimension is going to match up with what you were missing here in the Pythagorean theorem. Okay, so let me just wrap up then. So the main idea here was to add an extra special dimension to the projected points that is equal to the distance to the subspace. Yeah, so you found this k over epsilon squared dimensional subspace. You projected all your points onto it, and then you added one extra dimension, which encoded this distance. So all of these points live in a very low dimensional subspace, say k over epsilon squared plus 1. So now I can apply existing techniques, now that they live in a low dimensional subspace, to get a Coreset for the kMedian problem, where I replace the dimension in that Coreset bound with k over epsilon squared. To answer queries, if someone gives me a set of centers, I put a 0 on the extra special dimension when I actually compute the distances. And putting this all together, we get a coreset of size k squared over epsilon to the 4th for kMedian, which is the first that's independent of n and d. And this dimensionality reduction technique is quite general, so it holds for other problems. For example, for subspace approximation, suppose I wanted to find a, my queries were subspaces of dimension k, and I wanted to tell you the cost of using that subspace. So like, what is the sum of distances to that subspace? The same procedure would work there. More generally, any other problem where the centers sort of fit into a low-dimensional subspace. Okay, so here is important that if I take the kmeans or the kMedians, they all live in a k-dimensional subspace, and that had to be a small dimensional subspace. Any other problem where that happens, you can apply the same kind of argument. What I didn't get into is you can actually compute these coresets in almost input sparsity time. So there are, as I said a few times, there are fast approximation algorithms for computing sum of distances to a subspace. Some work that I have actually with Anish and Rory. So these can be made efficient. So that's all. Yeah. Any questions?
So your coreset was unweighted at the end?
What's that?
Your coreset was unweighted at the end? Like, you didn't have weights in the coreset?
Yeah, we don't actually need weights here. Yeah. I mean, well, actually, it's like it depends, like what what you use for the black box, right?
Yeah.
So like, but there are ways of doing it without weights. Yeah. So all I described was a dimensionality reduction procedure, which gives the space. And now you apply whatever you want to do this. There are a lot of coresets that sample, and when they sample, they have probabilities, and these probabilities, one of the properties become the weights. Sometimes you can fold those into the costs, other times you can't. So yeah. Question? Yeah.
Just to make sure I understand. So you can pre-process with Johnson, Lind, and Strauss, or you can't for these problems?
For k-means, it's clear that you can, because you just care about these pairwise distances. And so you can pre-process down to like log n over epsilon squared dimensions. For kMedian, it's much less clear, right? Because so I mean, there's some recent work of like Ilya Rosenstein and others, which has some results for dimensionality reduction for kMedian using by Lipschitz embeddings, but it's not at all clear that you can just do this with Johnson, Lind, and Strauss. Yeah. Question? Yeah.
You described one of the applications being for streaming situations.
Yeah.
Can this? It sounds like you want to have all the data, compute the whole dimensionality reduction, and then use that to compute these sparse approximations, or am I misunderstanding?
You need all the data to, so in the streaming application, you would like take maybe the first twice the coreset number of points, and you would apply a coreset to them to reduce the number in half.
You can combine different coresets that are different low-dimensional subspaces.
Yeah, I mean, so that was like very, exactly. Yeah, exactly. Yeah, I didn't describe how these are composed, but you can do that. Yeah. Question? Yeah.
About the other application for the distributed setting.
Right.
If every server returns you k, a set of k, coreset of size k, at the end you have a super good coreset in the centralized thing.
Everyone is giving a coreset of size k. That's not the same k as the parameter k, or it is?
How close?
How what?
I think it is.
Oh, it's not the same k. Like you can show that you actually need like k over epsilon.
Sure. But
yeah.
Okay, k over epsilon.
Okay.
It's the same k for everyone. So at the end you have number of servers times k.
Which is huge, right?
Yeah.
But then you could apply a coreset to that again and reduce it down to the size of any coreset. Yeah.
Okay, but maybe n. Maybe this k times. So you end up to have.
Yeah. So you end up with like number of servers times the coreset size.
Yeah.
That's the total amount of information that goes to this central server, and the central server can either choose to use that or it can choose to apply a coreset to it on top of it. Yeah. if you'd like not to like sort of overload one particular server, like you could imagine like having a tree of these things by like pairing them up and reducing it along the way. Yeah, Anesh, yeah.
So when you compose these coresets, do you have to add this extra dimension every time you do one composition?
Yeah, so you, that's right. Like, well, I mean, it's like, it's an extra dimension for each of these things. But then, like, your coreset size becomes, I mean, like, if I have two coresets, then what I can do is I can lift them back up to this original space, and then I can apply this coreset on these, and I unfold the weights. So I have all my points in this d+1 dimensional space. I can then apply a coreset to reduce it down to k over epsilon squared, and then I add one back. So it's not like that one is accumulating, if that's the question. Yeah.
Can you do this unfolding efficiently? Like, are there extra algorithms to go from the coreset itself to all the points?
Well, they live inside the space, right?
Well, I mean, like, you don't need the original endpoints, right? Like, you just need, you have, so you do dimensionality reduction, and then you get some small set of points and weights, or sometimes, depending on whatever algorithm you use. And then you also, you're storing this space S, this description. And now, I can map the points back to this original space, given this, and I map them back, but I still have a small number of points. And now I apply, the coreset on top of that. Yeah. Okay. Any other questions? Okay, cool. Thanks.